we are going to discuss about EMF, internal resistance small r, terminal potential difference capital V of a given cell. This is diagram here. Cell. This cell has terminal potential V, and this is internal resistance small r. These are two electrodes here, and this is electrolyte. So this R is external resistance is connected across the cell. Switch is given here. So let us check the definitions first. So what is internal resistance of the cell? So resistance offered by a electrolyte of the cell to the flow of ions. So it is the resistance offered by the electrolyte of the cell to the flow of ions. This is called internal resistance. So here in this diagram, so ions will flow here, plus minus ions. So here some resistance is offered by the electrolyte, which is called internal resistance, depicted by a small r. And this is EMF, electromotive force. So this is potential. Electromotive force is potential. The potential difference between the two electrodes of the cell when no current is drawn by the cell is called EMF. So basically it is nothing but when this circuit is off, no current is flowing in the circuit. So at that time the potential difference between these two, when there is no current flowing in the circuit, that means this switch is off, that is called EMF. Now next is terminal potential. So the terminal potential difference is potential difference between the two electrodes of the cell when current is drawn by the cell. Here terminal potential is, so when this switch is on here, then current will flow in this direction. Suppose current is coming in this direction, I. So some voltage is drop here IR drop, here also capital I into R drop. This is, so potential is drop across the internal resistance, also across the external resistance. So what is terminal potential? When current is flowing in the circuit, switch is on, the measurement of potential difference between the two electrodes is called capital V. When no current is flowing, EMF. When current is flowing, terminal potential. So here it is found that EMF is greater than potential difference. Here let key capital K is on. So at the time I current is flowing in the circuit, so expression will be total EMF is drop across terminal potential and drop across this is an external potential drop, this is internal. So external is I into R, internal is capital I into small r. IR is potential drop across internal resistance small r, is called lost voltage. So here I can be calculated here. I is EMF by total resistance, which is R plus external plus internal. Also expression can be written as, so V, taking V on the left side, so it will be U minus V on the right side, IR. So small r from here is E minus V by I. So in place of I we can write V by R. So finally this will be here E by V. So this R is taken here, E by V, V by V. So V cancels out. So this expression is small r, internal resistance equal to E by V minus 1 whole into resistance, external resistance. So this is EMF by terminal potential minus 1 into external resistance capital R. So this is the expression for small r. Now here emitter, its definition is it has low resistance and is connected in series to measure current. Ideal emitter has zero resistance. So emitter is, its function is to measure current, so it has low resistance, is connected in series. Voltmeter is high, it has high resistance, connected in parallel to measure the potential difference across a device or resistor. So ideal voltmeter has infinite resistance. So let us solve some problems here. Find RAB, resistance across, resistance between, total resistance between R, A and B. So this is the figure given here. We have to find out the total resistance across AB, point AB. So in this case, what we have to do is first check this one. These two, this is R1 and R2, they are in series connection because they are connected like this. So this is R1 and this is R2. So they are connected in series. So its value will be R1 plus R2. So here R1 and R2 are in series. So their total value is R1 plus R2, which is 6 ohm. So we can name this by any name. So I have named here R12. So this circuit can be replaced by R12 here. This is second figure. So here I have replaced with R12 here, value is 6 ohm. Now these two are in parallel. Connection type is parallel. So R12 and R9, they are in parallel connection. That's why formula will be 1 by R12, 1 by R2, its total value will be. So I have named here the total value coming, I have given the name R1 dash. So this will be 1 by 6 plus 1 by 6, which is 1 by 3. So final value is R1 dash. So replacing these two with R1 dash here, R1 dash, which is 3 ohm. Now here R1 dash, this is 3 ohm, and R3, they are in series connection. So series connection here, R1 dash, R3 in series. So total value will be 3 plus 3, which is 6 ohm. I have given here R2 dash name. So it is replaced by R2 dash here, 6 ohm. Now in the figure, new figure, these two are in parallel now, R2 dash and R8. So R2 dash, R8, they are in parallel. Formula will be, formula is 1 by R2 dash plus 1 by R8 equal to, so its total value I have given name R3 dash here. So 1 by R3 dash equal to 1 by 6 plus 1 by 6, which is 1 by 3. Its value is 3 ohm. So this whole parallel connection is replaced by R3 dash here. So this is R3 dash 3 ohm. Now these two are in series connection. These two are in series connection. So combine these two, R3 dash and R4, they are in series connection. Now here total value will be 6. So I have given them R4 dash. So in place of this circuit, we can replace this part with R4 dash here, 4 dash, and this is R7, this is R5, R6. Now these two are in parallel. So R4 dash R7 in parallel connection. So this will be R4 dash 1 by R4 dash plus 1 by R7. This I have given name R5 dash. So its final expression will be 3 ohm final value. So replace this part with R5 dash. So this is R5 dash, value is 3 ohm. Now these two are in series. R5 dash and R5 they are in series. So R5 dash, R5 they are in series. So value is 3 plus 3, 6 ohm. This is R6 dash, name is given as R6 dash. So final figure here will be like this. One R6 here, other one is R6 dash, which is 6 ohm. So by looking at figure, it is clear they are in parallel connection. R6 dash, R6 they are in parallel. So formula will be, so resistance between A and B will be 1 by 1 by, or we can directly apply this formula, R6 dash into R6 by R6 dash plus R6. So final answer is 2 ohm. Final figure will be like this. This is A terminal, this is B terminal, value will be here 2 ohm. Value here is 2 ohm. So this is the final figure. Find RAB. Here also you have to do in a similar manner. So here these two are in series. So they are in series. So value is 10 ohm. This is R1 dash. Here name is given as R1 dash. This is R3. So now they are in parallel. So step by step we have to write the answer and change the figure also. Like R1 is replaced here, R1 is given here. Now R1 dash, R3 dash in parallel. So replace this part with R2 dash. R2 dash is 10 by 3. Now all these three resistors R1, R2 dash and R2 they are in series. So R1, R2 dash, R2 they are in series connection. So direct addition. So 10 by 3 plus 5 plus 5, which is this will be 40 by 3 ohm. So resistance between A and B is 40 by 3 ohm. Now here also resistance between A and B you have to calculate. So first of all, this 1, 2, 3, 4 and this 7, 8 and 5, 6 they are in series. So combine all this. Series means just take addition and give name R1 dash, R3 dash, R2 dash, something unique name. So 4 ohm, 4 ohm, 2 ohm, 2 ohm. So new figure will be R1 dash, R3 dash, R2 dash, R4 dash. So 2 ohm, 2 ohm, this is 4 ohm, 4 ohm. Now these two are parallel, these two are parallel and these two are parallel to each other. R1 dash, R2 dash in parallel, R3 dash, R4 dash in parallel. So value is here 4 by 3. So new name is given as R2 double dash. Here also 4 by 3 ohm, R2 double dash. So here figure will change like this. This is R1 double dash. This is R2 double dash 4 by 3, 4 by 3. Now they are in series connection. So direct addition is here. So final value is 8 by 3 ohm. So find the current in this current we have to calculate. So potential is given here. So to calculate this current we have to calculate the total equivalent resistance of this circuit. So let us calculate. To calculate I value of equivalent resistance capital R is needed. So we have to calculate. Now let us redraw the figure here. This figure can be changed like this. This is R1 and this is R2. So this is R3, R4, R5 and R6. Now these two are in parallel and these two are also parallel. They are in parallel. So here R1, R2 parallel, R3, R4 they are in parallel. First combine these two, this 4. So this is 1 by 2 ohm, this is 1 ohm combining. R5 and R6. Now this is R2 dash, R3 dash. Now R5 and R6 they are in parallel. R5 and R6 they are in parallel. So this is R5 and R6 they are also in parallel. And these two are also in parallel. R1 and R2. So figure will be like this. This is R1 dash, this is R3 dash, R2 dash. So finally here, now these two will be in series. R2 dash, R3 dash they are in series. Like this, R1 dash, R3 dash series. So R1 dash, R3 dash. So now they are in parallel. So total parallel value will be 2 by 5 ohm. Now here total value is 2 by 5 ohm. So now we can calculate current here by Ohm's law. By using Ohm's law, what is current? Current is V by R by Ohm's law. So V is given as 6 volt and resistance we have calculated 2 by 5. So this is 30 by 2, 15 ampere current flowing in the circuit. Now next topic is temperature dependence of resistivity. So resistivity depends upon the temperature. So we are let temperature T1 resistivity is suppose rho 1. At temperature T2 resistivity is suppose rho 2. Now here it is observed rho 2 minus rho 1 is directly proportional to rho T2 minus T1 into rho 1. So this value difference in the change in resistivity depends on change in temperature, also on rho 1 initial value of resistivity. Now this is delta rho, this is delta T and this is rho 1. Now they are proportional. To make them equal, we have one constant is multiplied here. So which value is, this is called coefficient of resistivity. So this is coefficient of resistivity. This is rho 2 minus rho 1 by rho 1 into delta T, which is T2 minus T1. So if this can be converted to in this formula, because resistivity can be written in the form of resistance and length by length area format like this. L by A. So using this, so this L by A they will get cancelled out. So here this is R2 minus R1 and in place of rho 1 this will become R1. This is delta T, T2 minus T1. This alpha is called temperature coefficient of resistivity or resistance. SI unit is per Kelvin. For metals and conductors, alpha is positive S because rho increases with increase in temperature. So resistivity increases with increase in temperature in case of metals and conductors. Here, for example, for copper it is 0.004 per degree centigrade. So change in resistivity is 0.004 per degree centigrade. Here for alloys, alpha is small but positive. for this 0.0001 per degree. Now here we will discuss little bit about failure of Ohm's law. Ohm's law fails when voltage V is not directly proportional to I. Suppose this is theoretical value, V directly proportional to I. In this direction it will go straight linear. Now in the experiment, if we get like this, if the curve is not linear, then the devices which obey Ohm's law is called ohmic device, like metals, alloys, etc. Devices which do not obey Ohm's law is called non-ohmic devices, like diodes are there and transistor, where V is not directly proportional to I. Here they are not exactly proportional to I in case of diode and transistor. So this is our lecture part 1 of current electricity. Now we will move to next part. Current density, symbol is J. This is also written as small j. So what is current density? It's a current per unit area. That means current flowing per unit area of cross section of a conductor is called current density. So unit is obviously current by density, that means ampere per square meter. We know that by Ohm's law V equals to IR. So this is I, R can be written rho L by A. So here V by L being L here, 1 by rho here. So this is electric field, this is conductance, and this is current density because I by A. So current density can be written as like this, conductance into electric field is current density. Now this can also be expressed in terms of NA square tau by mass of, this is mass of electron. Now this is also mass of electron. This is NA square tau electric field, mass of electron. Next topic is electron mobility. So it is defined as the drift velocity per unit electric field. So drift velocity per unit electric field. So when electric field is applied across a conductor, so how much is a drift velocity experienced by free electrons, that is called mobility. Unit is meter square per volt second, this volt second. Grouping of cells. Here cells we have already discussed. Now here we can make them in series or parallel. So let us discuss about series. So there are n number of cells connected in series like this, plus minus, plus minus, plus minus, and they all have internal resistance R, that means similar, and here external resistance is connected capital R. Now in this type of connection, total EMF will be N times E. This small is, this is EMF of one cell. So N numbers are there, so NE. Total internal resistance will be, so plus plus R like this, so N times, so series resistance NR. Total equivalent resistance will be external plus internal. External is capital R, internal is N times R. So what is current flowing in the circuit? Total EMF by total resistance. Total EMF is N times E and total resistance is capital R plus NR. This is the expression for electric current. Now here we have two cases. Case 1, when R is greater than this value NR. So external resistance is very high here. So in this case this can be neglected. So NE by R, So this can be written as N times E by R. This is current produced by single cell and N times. So when this kind of consideration is there, R is greater than NR, very higher than NR, then current becomes N times the current due to single cell. So current is N times current due to single cell. Second case, when this is very less, so this equation number 1 will be, this can be neglected. So N E by N R, N cancels out like this. So E by R, this is current produced by single cell. So current due to, this is low current due to single cell. So here, to draw more electric current from a series combination of cells, high external resistance is required. So when R is very high, then only you will high current is drawn from the cell. If R is less compared to NR, then current drawn will be less. Now cells in parallel connection. When these cells are in parallel connection, let us see in this diagram. So n numbers of cells are there, they are connected in series of parallel connection. So they all have internal resistance small r, current flowing is capital I, like this. External resistance is capital R. So here total resistance will be parallel, expression of parallel is 1 by R plus 1 by R plus 1 by R, this will be N times by R. So Rp, internal resistance of parallel connection will be R by M, small r by M. So that is, what is electric current? Electric current is here, they all are in parallel connection. So EMF is same. EMF is same because of the parallel connection. So total EMF will be E, and total resistance will be external plus internal is Rp. So this is E by R plus small r by M here. So what is M? Number of cells. So M E by M capital R plus small r. This is expression of current drawn by external resistance from the cell. When this M number of cells are connected in parallel. So case number 1. So when MR is less than small r, then this will be M E by R. This equation becomes, current becomes small m E by small r. M times the current produced by single cell becomes M times. So this is M times E by R, current produced by single cell. When MR is greater than R, so equation becomes, this M gets cancelled out, E by R, current produced by single cell. So from here we can conclude, to draw more current from parallel combination of cells, external resistance should be small. So in parallel connection of cells, external resistance should be small to draw more current from the circuit, more current from the cell. Here efficiency of cell is, this is efficiency symbol, so power out by power input. So this is I square R, and the external circuit current is I, so I square capital R. In input value is, total input is total current into total resistance. So I square into total resistance is R plus R. So this is efficiency of a single cell. So N will be I square R by I square plus I square capital R. So I square cancels out. So this is capital R by capital R plus 1. This is efficiency of cell.